Okay, I'll start the class. This is the second TA session of Structure Analysis 1 taught by Professor Amit Shah. I am Trisha Chakraborty, one of the course teaching assistants, and I am a PhD student at the Indian Institute of Science, Bangalore. As we discussed in the last class, there are three common types of elements in the 2D plane, in 3D plane as well. But we are right now for the first most of this course we will only look at 2D objects. The basic laws or the basic methods of solving the problems will be similar in 2D and 3D planes, but the 2D ones are possible to be done by hand, and for 3D structure analysis, we generally use softwares. So this course is mostly about two-dimensional objects. The first type of the simplest type of element is a truss element. It transfers only axial force. So in the last class again we have seen there are four types of forces: axial force, and axial force is when the force is along the length of a member, and torsional moment where the moment this is a torsional moment, so it is the sense is also along the length of the member. And then there are bending force and bending moment and shear force when the shear force is transverse to a member, and then bending moment is the moment generated due to transverse force. So truss element transfers only axial force, beam element transfers only shear force and bending moment, and frame element transfers axial force, shear force, and bending moment. Now, an element is a truss element or a beam element or a frame element depending on the kind of loading. There will be no difference in the physical physical appearance of any of these elements. They will be the same. They will be by an element we mean uh, a beam or a column. See, now when we are looking at when we are designing a building, we use the terms beams, columns. That beam and this beam element is slightly different. Those are the structural beams and columns are the functional terms that we use in a building, and these are purely based on the kind of loading on coming on this element. So if we have an element that only has axial loading, we will treat it as a truss element and solve it in that way. And if suppose there is a truss element, and suppose I have a beam element where there is only transverse loading, then the only types of forces being generated there are shear force and bending moment. But if I apply an axial force at its end, then it will become a frame element. There will be no change in the physical uh, in the element physically, but but our treatment of it will change in structural and from the structure analysis point of view. So frame element is a generic one. It is a kind of combination of truss and beam element, and today we are going to look at truss elements. So, what is a truss? Firstly, it is a framework that supports a structure. For example, a roof or a bridge or factory sheds. These are the most common. The roofs of factory sheds, and this is a. I think this is the Howrah Bridge. This is a 2D truss. This on this edge, that edge also there is a 2D truss, and then they are connected. And this is a very simple truss triangle. This part is a truss, and on top there is the see. This is a truss. This is a truss, and see there are rows of trusses. Then there are these beams lying atop the trusses, and then there is a roof resting on that. So the truss is what is basically holding the structure up. This is a truss bridge. This is a truss roof. Formally, now, from the mathematical point of view, truss is an assembly of two force members connected by nodes that creates a rigid structure. We need to define what a two force member is. It has pins or hinge supports at both ends. It does not carry any load in between, and it can only have two forces acting upon them at the hinges. So this is an element. We have seen what a pin or hinge support is. It is a support that restricts displacement in both directions. Now see, firstly, when we were looking at free body diagrams last time, or we saw that in a pin support we said that for a pin or hinge support it restricts displacement in x direction and y direction, but it does not mean that it is actually the horizontal and vertical direction necessarily. It means that it, even if the member is inclined, it what we mean by x direction and y direction is basically any two mutually perpendicular directions. So if the member is inclined, The pin support will not allow displacement. See, the if displacement is not allowed in any two perpendicular directions, it means there is no displacement overall. So a pin support does not give any restricting moment, but it restricts displacement in all directions. So near two force members, there are pin or hinge supports at both ends, and it will carry no load in between. What is meant by in between is there will be no transverse loading on the member. There will only be forces at the hinges, and they will be in the axial direction, that is along the truss member. So if the truss member is inclined, the only forces will be along this line. That is a two force member. And so this is the member is only under axial loading, no shear, no bending, no torsion. This is what an inclined truss element. These are pin supports. So there can be, see, forces. The forces can be applied in any direction, but the resultant of all these forces must be along the AB direction. Types of axial loading. There are two types. Obviously, tension that attempts to elongate a member. It is very easy to visualize. If the it's a pulling kind of force. So if the both ends have forces away from the member, it's a pulling effect. So that is tension. And compression attempts to shorten the member. So here the both these forces have to be towards the into the body. And to maintain equilibrium, since each member of a truss, see, this truss element is in equilibrium, it is very obvious that the resultant force at this end and the resultant force at this end must be equal in magnitude and opposite in direction. So tension is when both the this T and this T are pointing away from the member. Compression is when the C is pointing into the member. Now, this is an see, and another thing that is very important to think about in civil engineering is we see structures around us that are very complicated. So, we have to, as engineers, not just civil engineers. The purpose of engineering is to simplify real real world problems in a manageable to a manageable degree, so that we can work with them. So idealization of civil engineering structures is important. This is a truss bridge. This is a truss. Then that on that end there is another truss, and there will be some kind of transverse beam elements, and there will be the deck, and the car or the passenger people will pass through here. This is called a through truss because the deck is at the bottom of the truss. So the idealization is we can take this part and the part on the other side as two individual 2D trusses and analyze them. So you can see that this has been idealized as this, trying this is this member, this vertical member. So there are vertical members, horizontal members, and inclined members. This is an idealization. Classification of trusses. A simple truss is constructed from the basic triangular element by connecting two members to form an additional element, like this. First I'm forming, so at any now the another thing I have to mention is that between any two members, these are all hinged or pin. So they are all called nodes. A, B, and C are nodes here. There is a basic triangular element. Now this is rotationally not a stable structure, so we have to add another two members. This is the simplest truss we can have. Then after this, suppose I want to add another node, two more members, another node, two more members. So this is how the truss is expanding. This is a simple truss. A compound truss is constructed by connecting two or more simple trusses using hinge or additional members. So this is one truss, this is one truss, and they are connected by these kind of members. So this is a compound truss. Now this is one simple truss. A, B, C is one simple truss, and there are members inside. C, E, D is another simple truss, and they are connected by this member. So this is a compound truss. This is a simple truss. This is a simple truss, and the whole thing is a compound truss. And complex trusses have a polygonal structure. They are neither a simple nor a compound truss like this. So generally we work with simple trusses when you are given problems to solve, but the methods of solving stay same irrespective of the type of truss. Stability. External, there are two types of stability: external, internal. External stability means that the truss must satisfy three equations of equilibrium. Now this should actually be two, because in the 2D plane, sorry, this is three. The three equations of equilibrium are that sigma fx should be 0, sigma fy should be 0, and sigma mz should be 0. Sigma means the summation of all forces or moments along in that sense. X and y, again, you need not take x and y in the horizontal and vertical direction only. You can take it on any two mutually perpendicular directions. So the three equations of equilibrium must be satisfied. All support reactions must not be parallel. If that happens, suppose I have a, let me see if I have a diagram. Yeah, here. So suppose I have this truss, okay. So it has a roller support here, a roller support here, a roller support here. So all in at A, B, and C, the support reactions will all be in the upward direction, in the upward or the downward direction. So the displacement in the in this direction, a vertical direction is restricted. But what if I apply a horizontal load? If I apply horizontal load, the truss will simply roll to this side. Like it can roll because there is nothing to take to resist a force in the horizontal direction. So all support reactions must not be parallel, and all support reactions must not be concurrent. Concurrent means passing through a same point. So suppose the truss has this kind of rollers. We know that roller support basically provides a reaction perpendicular to the surface it is lying on. So this is the surface. So it will, the RA will be perpendicular to this surface, RB is vertically upwards, and RC is perpendicular to this surface. And suppose all three of them pass through this point C, then what will happen is if I apply a vertical loading, it will be resisted. If I apply a horizontal loading, RA and RC will have components in the horizontal direction, so that will be resisted. But what if I apply a moment about C? If I apply a moment about C, the truss will rotate like this because the moment cannot be resisted. So all support reactions must not be parallel, all support reactions must not be concurrent, and of course the equations of equilibrium must be satisfied as in any body. Internal, no part of truss can move rigidly relative to another part. Number of members required for geometric stability, this is a formula. One sec. Baba, hello. বাবা আমি ক্লাস নিচ্ছি, আমি তোমাকে পরে ফোন করছি, নটার পরে আমার, ঠিক আছে? ওকে, টাটা, সাবধানে থেকো, ভালো। ওকে, সরি অ্যাবাউট দ্যাট। There is a formula of the minimum number of members required for geometric stability. M is the number of members required. J is the number of joints. Joints are all those. Okay, and here A, B, and C are also the joints. The support, all the points between two members are joints, or all the points where more than two members are meeting are joints, even if they are support points. So this has 1, 2, 3, 4, 5, 6 joints. So going by this formula, 6 into 2 is 12, minus 3, 9. So this truss needs to have 9 members for internal stability. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the bare minimum required. There can be extra members. For example, I can put a member between these two joints. So that will be stable. So this M is the minimum number of members required for geometric stability. And members must be arranged such that the truss can be divided into triangular blocks, no rectangular or polygonal blocks. So again, let's look at an example. Yes, this one. Suppose this is, okay, how many joints are here? 1, 2, 3, 4, 5, 6. This is not a joint. Okay, this is no, by just by seeing you cannot say. I am just saying suppose these members are overlapping and not actually passing through each other. So in that case there are 6 joints. So now 9 members are required. Look at the number of members here: 1, 2, 3, 4, 5, 6, 7, 8, 9. So this truss does have 9 members which I need, but the way they are arranged is that this part of the truss is overly constrained, and this part does not have any like cross member. So this is a rectangle. So what happens here is there is an internal kind of instability. If you can imagine that it can fold into itself, like if I suppose give a force, apply a force in the inclined direction here, this part will not be able to hold up. This will, the externally the truss will be stable, there will be no overall rigid body motion, but there will be an instability. This part will compress into itself. So what I should do to make this truss stable is take one of these members and put it here or here. In then it will be, both the parts will be all there will be four triangular parts, and it will be a stable truss. And externally it is stable because if I put a horizontal loading, this hinge will be able to resist that, and if I put a vertical loading, both these will be able to resist that. So this truss will be stable if I take one of these members and put it in this part. So the presence of rectangular block makes it unstable. There are two categories of analysis methods for determinate truss. Determinate means that we can solve a body. It can be truss, beam, frame. All the term determinate is applicable to all the types of members. Determinate is when we can solve the structure. Now solving the structure means solving the forces and all at all in all the members. So from that I can get the stress in all the members. That is what solving the structure means. So to solve it, if the equilibrium equations are alone enough, then it is a determinate truss. And if it is an indeterminate truss, that means it is overly safe. It has more members than required, or it has more number of reaction forces than required. So, for example, this is a 2D body. It has three equilibrium equations, so it has to have three forces, like three reaction forces. So it has one here in the horizontal direction, in the vertical direction, here in the vertical direction. It has three forces, three reaction forces. Now, suppose both of these were hinged or pinned, then there will be four support reactions, and we will not be able to solve it when we are solving the support reactions. Like we saw last time, the first step of solving bending moment diagram or shear force diagram is solving the support reactions. So what if there are more than three support reactions? We will not be able to solve, because then the number of unknowns will be greater than the number of equations. So that is an externally indeterminate structure. For that we have to have some extra information, which we'll look at later on. I think the second half of this course deals with indeterminate structures. And to make it for example, and to make it internally indeterminate, I suppose this part is internally indeterminate. If I had one member here and there are two members here, so the minimum number of members required is 9. But if I had 10 members here, then I will not be able to solve it by the simple methods, these two methods, method of joints and method of sections. For that we will need extra information like the geometric properties or the material properties. So the first step is deterministic trust. That means it is just about stable. It is stable, it is in equilibrium, but it is not extra stable. And in the physical world, all structures that we make are indeterminate, because indeterminate means extra stability, extra safety. So in civil engineering, it is of course always better to be safe than sorry. So we try to put in a lot of indeterminacy into the structures. But when we are doing this basic course, the first thing we look at is solving determinate structures. Method of joints. It is suitable when forces in all members are to be calculated. This is the method of joints and method of sections are this method we generally apply in if you are writing a theoretical or subjective exam. When you are given a big truss and you are told to solve a lot of the forces in a lot of members, we look this method is more suitable. While in competitive exams like gate, they can't ask you to find the forces in 5 6 members. So generally what they ask is one or two members. Then the method of sections will be applicable, will be convenient. Both of these methods can be applied in all determinate trusses, but the one which you choose depends on what you are actually looking for. So method of joints is suitable when the forces in all members are to be calculated. At each joint there are two equations of equilibrium. Now see, from an overall structural point of view, there are always three equations of equilibrium: x direction, y direction, moment in z direction. But when we are looking at one joint, a moment at that point is irrelevant, because all the joints as we have seen are hinged or pinned. So hinged or pinned supports do not give any moment resistance. So there is no point in writing an equation about the moment about that joint. We know it is zero. So we have two equations of equilibrium, that at every joint the summation of forces along two mutually perpendicular directions should be zero. So sigma fx equal to 0, sigma fy equal to 0. As I said, x and y are just representatives. They need not be horizontal and vertical. They can be, generally when we are actually working with trusses, we take along this line and along the length of the truss and along perpendicular to that you can take. Any two perpendicular directions you can take. This method cannot be applied if the number of unknown forces at a particular joint is more than two. So we have to choose joints in such an order that the first joint which we address has to have only two members meeting at that point. Then once we solve one of those members, we can go into another joint which maybe has three members meeting at that point, but one of the forces we already know. That way, from joint to joint, we can move ahead. And the sign convention, as always in structure analysis, in every part of it, the sign convention is very important. In bending moment and shear force diagrams, we have seen there are pretty specific sign conventions, and here forces in a members are shown by double arrows. For tension, arrows point away from each other. For compression, arrows point towards each other, and tension is said to be positive and compression is said to be negative. Again, there can be no universal sign convention. It depends on what convention you are using. So I would suggest that in subjective exams for your college or something, or if you are writing a subjective exam somewhere else, mention the sign convention in all the questions. Even if it is the convention, this is the, like, tension is positive and compression is negative in almost all books you will find. But even if you are using that, I would suggest, yes, please solve the problem. uh, what do you mean? Week, I didn't get what you are saying. Week one, you mean the bending moment and shear force diagram, those problems? You can unmute and speak if you want. Okay, if you have something to say, say it in the chat box or unmute and say. I'll continue right now. So yes, as I said, just mention the sign convention which you are using, and if it is an MCQ question or in a competitive exam, you have to follow the conventional ones. That is, tension is positive, compression is negative. Zero force members. If at the joint three members meet and two members are collinear, and there is no support reaction or external force at that joint, then the collinear members, non-collinear member will carry a zero force, like this. Look at this point, this node C. So there are two collinear. We know the collinear members. This AC and CB are collinear members. They are along the same line basically, and there is one non-collinear member, CD. There is no force applied at this point, there is no support at this point. So if, suppose, just assume that this member has some force F in it, in this. Okay, so this force is, suppose if it is a tensile force, it will be away from the member, so in this direction. But, and there will be some force here, some force here. Now when you are looking at studying the equilibrium at this point, when we are looking at sigma Fy equal to 0, if this is x direction along ACBA, this is the x direction, this is the y direction, then when I am doing sigma Fy equal to 0, I see only one force here along this CD, and there is nothing to balance it out, because FAC and FBC are both along the x direction. So there is no one to balance out the force along CD. So there can be no equilibrium if FCD is non-zero. So that means that if there are two collinear members and one non-collinear member, this one has to have cannot have any force in it. So this is a zero force member, CD. Here, look at this CD is a zero force member, because again here, if FCD is non-zero, then when I'm doing sigma Fx equal to 0, I will not be able to solve it. So FCD is 0, and when FCD becomes 0, it is as good as this member not existing. So remove this member from your diagram. Then you will again see that at this point D, there are two collinear members, DE and DB, and then DA is a non-collinear member, so FDA is also 0. So you can see that when you are given a truss, if you just keep an eye for zero force members open, you have straight away eliminated two members, and automatically the truss becomes a very simple one. It just becomes a simple triangular truss, so you can solve it much faster. So especially in time constraint exams, make it a habit of whenever you look at a truss, you should be able to identify the zero force members immediately and eliminate them. Identifying zero force members, here at at this point, these two are collinear, this is non-collinear, so this is a zero force member. If this doesn't exist, then at this point this is a zero force member. Similarly, from this side, this is a zero force member, this doesn't exist, so this is a zero force member. And at this joint there are one, two, three, so again this is a zero force member. Similarly, from this side you get these two. So you can see how much simple it becomes if you eliminate those initially. Eliminating means that you can remove it from your diagram, you do not have to include it in your analysis. And if by luck they ask the force in this member, you can just put it as 0. Now we'll solve a numerical example of method of joints. So suppose I'm given a truss like this. This is a Let's first see if it is a stable truss or not. So I know that for external stability I have to have three support reactions. There is a hinge support here, so there are two support reactions here, Ra and Ha. And at B it is a roller support, it has the reaction Rb in this direction. So there are three reaction forces, three equations of equilibrium. So externally it is stable and determinate. Then internal stability, what we saw is the number of members required is 2j minus 3. The number of joints is 1, 2, 3, 4. 4 into 2, 8 minus 3 is 5. And the number of members is 1, 2, 3, 4, 5. These two are different members. Okay, if D is a joint, then AD and DB are separate members. So I have 5 members. So this is an internally determinate and stable truss, and all we can see that both of these sections form triangles, so there is no problem. All the rules we have found so far, like we have seen for stable structures, hold here. So this is a stable and determinate structure, we can solve it. First step is to solve the external reaction forces. For that, we have three equations of equilibrium. One is summation of fx is 0, and we can see that the force applied overall on this truss is a W force in the downward direction. So sigma fx equal to 0 means there is only one force in the horizontal direction, HA, that has to be 0. Now I will do the summation of Fy as 0. So I'm assuming Ra and Rb are in the upward direction. So I will write Ra plus Rb equal to W, since it is in the downward direction. And as I said last time, when we are assuming the directions of the reaction forces, we don't actually know which direction the force is in. So we just assume something. If we and then we solve these linear system of equations, and then if we get Ra as negative, we have to reverse the direction that we originally assumed. So Ra plus Rb is W, and summation of m equal to 0. At this m, we can take about any point in the 2D plane. When we are conserving the moment, we can take any point. Here we take generally, but generally for simplification of calculation, we take the point through which there are maximum number of support reactions. So if I take A, I will see that the moment the moment applied by HA about A is 0, since it passes through the point A, right? We know that moment is the moment generated by a force about any point is the force into multiplied by the perpendicular distance from that point to that line of action of force. So if the line of action of force passes through this point A, then the moment generated by HA and RA about A are both 0. So I get a simple equation here. Only RB and W are applying moments about this point. So RB, it has perpendicular distance 2A from A. So RB into 2A, it is about the anticlockwise direction, and W, you can see W applies a clockwise moment about A, that is W into A. So this is minus. If this is plus, this is minus. RB into 2A minus W into A is 0. From that I get RB is W by 2, and putting this in this equation, I have RA equal to W by 2. Both of these are positive, so that means that RA and RB are both actually pointing upwards. And it is a symmetrical structure. Once you gain some experience in solving these kind of questions, you will be intuitively able to say that since this is the W is acting downwards and it is acting about the midpoint of A and B, and this is a symmetrical structure, RA and RB will both be half half. They will take half of each of the force applied. Now I'll look at joint A. What do I see at joint A? I will draw this like this. I see for two members here. As I said in one of the rules, you have to when you are starting to solve the stress, take one joint where there are two members. If there is a if you took this joint C, what will happen is there are three members. So there are three forces unknown to you, but at each joint you just have two equations. So you cannot proceed that way. So I took A. I'm drawing A here, and we know that trusses are two force members, so the resultant of the force through this member AD has to pass along this direction of AD itself. So if AD is a horizontal force, and if AC is an inclined force along this line, and this is 45 degrees, since you will see the geometric measurements of the truss has to be given. This is A, so we know that this will be 45 degree. The basic, you will need some basic trigonometry, some sine cos calculations in truss, because since you will encounter inclined members, so it helps if you just, I hope you guys already know the sine and cos of the basic angles like 30, 45, 60 and all, but just brush through those ones. So at A, FAD and FAC, I assume these forces, and since I'm taking these forces away from the joint, it means that I am, as since I'm drawing the free body diagram of the joint, basically I'm just picking up the joint and I'm looking at the forces applied on the joint. So if I'm applying a force AD on the joint in this direction, that means if I draw the free body diagram of the member AD, the force will be pointing towards left. Here it is pointing towards right, so on the member itself it will point towards left, so that it is away from the member. So basically it means that I have assumed that FAD is tension, I've assumed that FAC is tension. If I solve and get a positive value, I will say that yes, it was tension, and if I get a negative value, I'll say it was compression. So that means that when you are drawing the free body diagram of a joint, take the forces into the members, and to assume it as tension. That is what we generally do. So FAD is this, FAC is this, and HA we have already solved as 0, so there is no force applied in the horizontal direction. And RA we have seen it's W by 2 in the upward direction, so W by 2 I have written. Now I have two equations of equilibrium at this joint, sigma Fx equal to 0. Here I am taking the f, x and y as horizontal and vertical, but that is my choice. I could just as well have said this is my x-axis and the perpendicular one to this is my y-axis. You will end up with the same answer, and it will almost be the same calculation, because anyway this is an inclined member. You could just assume this is my straight and this is my inclined member. So sigma fx equal to 0. Let me see, I have to write down all the forces that have any component along the x direction. So FAD is along my x direction, so FAD I get full here, FAD. And FAC is in this direction, so it has one component along the x direction, it has one component on the y direction. So FAC cos 45 degree, and since they are both pointing towards the right direction, I am writing FAD plus FAC AC cos 45 equal to 0. From that, no, from the next equation I have to write. The next equation is sigma Fy equal to 0. So let's see what I have. W by 2 I have in the upward direction. Let's assume upward is positive. W by 2. Then FAD is along the horizontal direction and it does not have any component in the vertical direction. Okay, I should have mentioned that when I'm writing summation of Fx equal to 0, I should have mentioned that this force W by 2, it is along the y direction, right? So it does not have any component about the horizontal axis. So I only write FAD and FAC here. And when I'm writing the summation of Fy equal to 0, FAD will have no component in the vertical direction. I'll have W by 2 and I will have FAC sine 45 degree. You know this, right? That FAC component, if the angle is this angle, see these both are 45 degree, but if this was 30 degrees, then FAC's component about the x-axis would be FAC cos 30 degree, and its component in the vertical direction would be FAC sine 30 degree. So that is how it is written. This is just a simple, from this FAC you directly get as, we know sine 45 is 1 by root 2. So from that we get FAC is minus W by root 2. Since this is minus, it means that it is actually compression. So FAC is direction will actually be like this. It won't be this direction. And putting that value of FAC here, we get FAD is W by 2, that is tension. So I have solved the forces in AD and AC. Now I can move on to this joint C, because now since I know FAC, I only have two unknowns at this point, this DC member and this BC member. And similarly I can also approach from B, because at B also I have two unknowns. So I'm going to D. We can do any, and like the next joint you can take whatever whoever wants, people can take different ones. And at D we know, just now we were talking about zero force members. You can see that AD, deck DA and DB are collinear, and at this point, so that CD is basically a zero force member. So at joint D I just have one unknown left, this is 0, and I already know AD. If AD and if DA, like whichever side you come from, the magnitude will be same and the direction will be opposite, because this member AD is individually in equilibrium. So let's see. If AD here is W by 2, we solved FAD as W by 2. So, and we have solved it as tension. So we draw it like this away from the joint, as we, this is W by 2, this is FDB and this is FDC. FDC is 0, and since this is W by 2, this also has to be W by 2 by sigma Fx equal to 0. So this is also tensile force W by 2. Now we move on to the joint B. This joint has a support reaction of W by 2 upwards, and this FDB we have solved as W by 2 in tension. So again I have to draw this away from the joint. So see, the simple things that you have to remember is, if there is a tensile force, if you look at the body, the free body diagram of the joint, the force will point away from the joint. And if you look at the member itself also, at both ends the forces will point away from the member. Away from the member or away from the joint means tension, and into the joint or into the member means compression. So since this W by 2 is tension, in this joint I will draw this W by 2 pointing away from the joint. And I have a inclined member here FBC, this is 45 degree, and a reaction here. And you can probably see that in, since HA equal is 0, just forget about that this is a hinge. This part and this part are exactly symmetric. This diagram that I have drawn, W by 2 upwards, FAD here, FAC 45 degree inclined, this is also W by 2 here. This is 1 4, this is 1 4. This is exactly symmetrical. So we'll get the same value here. FBC is also minus W by root 2 compression. So this is the final diagram of the truss. These are the reaction forces. Here this AD and DB are in compression, sorry, in tension. This circle sort of thing means that this is a zero force member, and AC and BC are in compression. So these are the how the arrows are drawn. You generally won't be asked to draw the arrows like this, like drawing the joints here, or you can just take the member, and for compression you will show the arrows pointing inwards. For compression you can, for tension you will show the arrows pointing outwards. That is enough. There's another question. Method of joints. This is a slightly more complicated truss with more number of joints and members. So, as always, the first step is solve the support reactions. Let's anyway see for the stability and determinant part. There are three equations of equilibrium and three support reactions, two here, one here. So it is externally stable and determinate. And the number of joints is 1, 2, 3, 4, 5, 6. 6 into 2, 12 minus 3 is 9. So I need 9 members. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 members. It is determinate. It is stable. I can solve it by whatever we have studied up to now. And there are two forces applied here. Uh, now at this joint T, as we were looking at zero force members, see this is a TP and TU are collinear members, and TR is a non-collinear member. However, there is a force along this. There is a force that is not along this line. So TR is no longer a zero force member, because if I am looking at sigma Fy equal to 0 about point T, I will have something to counter. So this is not a zero force member. So as we looked at the rules, we have seen that At the joint, three members meet, two members are collinear. There is no support reaction or external force at that point. So this is, I just wanted to reiterate this point, that you should identify zero force members and eliminate them. But if there is an external force or a reaction, do not do that. So I'm solving the support reactions. If see summation Fy equal to 0. Again, since there is no horizontal loading, this horizontal force at Q will be 0, because there is no resistance, so there will be no force here. Summation of Fy equal to 0 gives me that Rp and Rq should add up and give me 60 plus 30, 90. And kilonewton is generally the unit used to quantify forces. You can write Newton, but in kilonewton we generally get more practical numbers, so that is what you will mostly find. And I am looking at summation mq equal to 0. Q About Q I'll see. So what are the forces that are applied? Okay, another thing I should mention, that see these, when I'm taking the moment about Q, I'm taking this 30, 60, and this RP. Now you might ask me that why am I not taking the force through SU? SU will also have some force, right? We just solved it in this question. Let's see. We just solved that these forces, these have, like, this has a force, this has a force. So when I took sigma summation MA equal to 0, why did I not take this force? That is because it is an internal force and it is balancing out. So there is FBC. FBC is not actually a force that can apply a moment about here, because it there is a FCB on this side, there is a FBC on this side. They are equal and opposite in magnitude. So internal forces do not apply moment about the structure. Otherwise, there will be no stability. So we only look at the external forces and the support reactions when we are solving the external reactions. Summation mq equal to 0. So let's see, these are all h. So rp is in this, in the upward direction, I have assumed, suppose. Then it applies a clockwise moment about q, and the distance, perpendicular distance, is 3h. So 3h into rp, and this 60 and 30, it applies anti-clockwise moment about q. So I'm taking it on the other side of the equal to. So 60 into 2h plus 30 into h. So rp, you just solve the rp, you can solve directly from here, 50 kilonewton, and rq is 40 kilonewton. This is not symmetric. Since the loading is not symmetric, and this is actually not, the structure is also not symmetric, so these are, the magnitudes are different. And let's start from joint P. Joint P has a support reaction of 50 kilonewton here, and it has two members, PT, two member forces, PT and PR. I'm taking them pointing away from the joint, so I'm assuming they're tensile. And summation of Fx equal to 0, I get FPT, and I get a component of FPR, cos 45 degree. From that I get a relation between PT and PR. And when I do a summation of Fy equal to 0, I get 50, and I get a this sine component of this FPR. So 50 plus sine, plus FPR sine 45 degree. From that I get FPR is minus 50 kilonewton. So it is, sorry, minus 50 root 2 kilonewton. So it is compression, since I got negative. And now when you put this into this equation to solve the PT, you have to put it with sign, of course. So just treat them as like we used to solve linear equations in two variables x and y. Just treat them like that. So when I put this, I'm getting FPT is 50. So this is tensile and this is compressive. Next, I'm looking at joint T. Can I look at T? There are three members meeting here, but I already know FPT, so I just have two unknowns and I can look at that joint and solve it. So at T, I have 60, there's a load here, there is a force TR that I don't know, there is a force FTU that I don't know, and TP, which I do know, 50 kilonewton, pointing away from the joint since it is tension. So sigma fx equal to 0. This is just a very simple. You can see that ftu will be 50 kilonewton tensile and ftr will be 60 kilonewton tensile, because there are just two forces along the two directions each. Next, joint q. At joint q there are just two members. So this is 40, and this is FQS. Solving in the similar fashion as here, we get FQS is minus 40 root 2, so it is compressive, and FQU is 40 kilonewton tensile. And let me see which members are left. I have solved these two, and these two. So I have RU and RS left. So I'm looking at joint S, FSU, FRS, and there is this force coming here. This I have solved. QS as minus 40 root 2. So I have taken towards the joint. See, since this is a compressive force, I have already solved it to be a compressive force. In the free body diagram, I am going to take this force pointing into the joint. So, sigma fx equal to 0, I have FSR plus 40 root 2, that the sine component of that equal to 0. Here I see basically both of these are pointing in the same direction towards the left side, so I have taken them as plus. You could also take both of them as minus, you will get the same result. If SR is minus 40 kilonewton, so it is compression. uh, Sigma Fy equal to 0, we get FSU equal to, since FSU is pointing downwards, since we are assuming it to be tensile, and this 40 root 2 has an upward component, so the cos component will be pointing upward, so we are taking FSU equal to 40 root 2 cos 45, so 40 kilonewton tension. So we have solved all the members. We know whether they are in compression or tension. From a truss, basically, that is all that will be asked from you. You will, if you are asked to solve a truss, you have to solve the external support reactions, and then you have to solve the forces developed in each of the members. You have to know whether it is compressive or tensile, and at max, if you have the cross section, if you are given the cross sectional area, you can just find out the stress by dividing the force by the area. It will be, we assume that, since in the very first slide, for in the beginning we had seen that there can be no forces in between the truss members. So at this point I cannot say that at the midpoint I'm applying another tensile load, nothing. So basically there will be a uniform axial force along the member, so there will be a uniform stress along the member. And why we are so concerned about stress in structure analysis is because whatever material we are using, steel, concrete, all of them have an yield stress. Okay, that means that suppose I am using steel which has an yield stress of 250 megapascal. That is a practical value. Megapascal is Newton per millimeter square. So I know that my steel structure has an yield stress of 250 MPa. If I apply if the stress developed in my stress member is more than that, it is going to fail. So my basic aim is that I have to solve the truss. I have to check the stresses developed in all the members, and I just have to ensure that the stress developed is less than the yield stress of the truss or yield stress of the material. So that is why we are concerned about the forces, because from that we get the stresses. We will look at all this later on. Right now we are just concerned about the forces. The the other method is method of sections. Yeah. So this is suitable when forces are required in only few members. So as I said, in exams like GATE, it is particularly useful. The whole truss is cut into portions via sections, and equilibrium of each portion is considered. Three equations of equilibrium must be satisfied in each portion. Unlike in the method of joints, when we are looking at joints, we are just looking at two equations. But here we are taking a 2D part of the truss. We are just as if cutting the truss and taking one part of it, that, and in that part we have to see that all three equations of equilibrium are satisfied individually in each portion. If I have a truss, I cut it, I take this side and I take this side. In both the sides individually, all three equations of equilibrium must be satisfied. Say summation fx equal to 0, summation fy equal to 0, and summation mz equal to 0. Mz can be taken about any point in fact, if you are taking a truss portion here, and you can take the take the point even outside that section. I hopefully will get an example here. And summation fx and fy, x and y, as always, you don't have to take it as horizontal and vertical, though we generally take it as that. You can take it along any two mutually perpendicular directions. So this is a truss. This is one of the just a very simple truss connected by triangular members. I'm cutting a section here. This section need not be perfectly vertical or perfectly horizontal. It can be anything. It can be an inclined section. So suppose I'm taking a section, I'm just cutting it. So I'm taking this side, I'm taking this side. So in the left free body, let's see what is happening. This part is, see, the part that is not cut is very obvious to you. You will just draw this part, and now since I have cut it like this, I have cut it through three members. So all three of these forces I've cut through. So basically, from I have to draw F H G FHD and FCD. These three forces I have to draw in the free body diagram, and I'm just drawing all three pointing away from the joints. So I'm assuming them to be tensile. And look at this part again. At this part, all these will be just as it is, and FGH, FDH, and FC. It's written CD. You can write it DC as well. So these forces I have cut through. So these so basically the forces that I am writing on this section and this section are the same forces. They will be in equal and opposite directions. I'm drawing it like this. So since I'm assuming all three of these are tensile forces, here I'm drawing in this direction, here I'm drawing in the opposite direction. This I'm drawing in this direction, here I'm drawing in that direction. So when I'm solving, I'll find a consistent way, so the internal forces are also balanced. So this is how a section is cut and the two halves are treated. Let's look at an example. This is this is a larger truss. In generally, in larger trusses, method of sections come handy because if you are going by method of joints, you have to look at a lot of joints consecutively. So suppose I want to solve. It actually depends on which members you are asked to solve. So if here I'm asked to solve these three members, so the very simple method is, if it is three, just we cut it in such a way that we are cutting all three of these members. Now I cannot find a way of just cutting three members, so I'm cutting it in a way like this. And I have to take two sections. One I'm taking like this, one I'm taking like this. So now the section which you have to cut, that will come to you from experience. Once you solve 5 6 questions, you'll understand which section to cut out intuitively. The first step, as we have seen always, it is common in both the methods. You have to solve the reaction forces. Here there is a horizontal force, so at this hinge support there will be an 5 kilonewton in the left direction. So H here will be 5 kilonewton, and suppose this is R1 and this is R2. So R1 plus R2 will be 5 plus 10 plus 10 plus 10 plus 5, that is 40. And now I have to take a moment about one of the points, and since there are two forces about this point, I am going to take moment about this point, so that I like reduce the number of moments by 2. The moment, there are so many forces here, so you just have to be patient and take them one by one. Let's see, R2 is pointing in the upward direction, so it is applying an anticlockwise moment about this point 1. And the direction and the distance is, there are six bays, 1 2 3 4 5 6. They're all 3 meter each, it's said. So the total length is 18 meter. So R2 into 18 in the anticlockwise direction. And now as I look at these forces one by one, we'll see that each of these forces apply clockwise moments about this point. So all of these I'm taking on the other side of the equal to. Look at this 5 kilonewton. The perpendicular direction of this line of action about this point is this 3 meter. So 5 into 3. Then I'm looking at this 5. The line of action of this 5 is this. So its distance is this 3. Okay, so like don't think these two threes are the same thing. One is is this distance, one is this distance. So 5 into 3, then 10 into 3 plus 3, because 10 is here, is along acting on this line, and this perpendicular direction is 3 plus 3 6, plus 10 into 9, plus 10 into 12, plus 5 into 15, 1 3 3 3 3 3. So this distance is 15. So this is the equation we get. From that we get R2 is 20.833 kilonewton pointing upward. Putting this in this equation, I get R1 is 19.1667 kilonewton pointing upwards. Now I have taken a section XX like this. So considering the, so I have taken a, you can take it doesn't matter however you draw the section. You can do it inclined, you can do it zigzag, anything. So when I'm drawing the free body diagram of this part, this part is intact. This R1H, these three members, and now I have, and this member is also intact, the 2 3, and then this force and this force are the ones that I have to draw here, as the section is intercepting them. So considering the equilibrium of LHS, the left hand side of XX section, and taking moment about joint 1. So now see, when you have, 1 second. Yeah, so I have Just 1 second. Okay, sorry, we are. So this point 1 1 that is here, why am I choosing such a point? See, in this 1 1 is not included in the section. It is lying outside the section that I've drawn. But I'm choosing 1 1 because it is a convenient point. I have four unknown forces basically that this section is cutting through this member, this member, this member, and this member. But all three of these members happen to pass through this one point. So if I take the moment about this point, the only unknown I have from the left hand side is this force in this member 3 4. So if I am naming it as FC, so FC into 3, this distance is 3. FC is in the horizontal direction, and the perpendicular distance from 1 1 is 3 meter. So FC into 3, and then forget about everything that is happening on the right side of the member. So this of the structure, so this 10 10 5, this support reaction, they are not relevant here. I'm just looking at this side. So I have a reaction R1, and about R1 into 6. R1 into 6, I'm getting 1. I'll just look at the senses as well. I'm taking FC in this direction, in the right direction. So it is clockwise about 1 1. R1 also gives a clockwise moment about 1 1. So it is R1 into 6, and this 5, and this 5 also gives a clockwise moment, 5 into 3, but this 5 gives an anti-clockwise moment. So this is on this side, and this H, this horizontal reaction also passes through 1 1, so it doesn't have any component, neither do all these three forces. So this is my equation. FC is minus 38.33, that is a compressive force, and if A here is a zero force member, A, B, and C, I was supposed to solve A, B, and C, and A, you can see it is already a zero force member since these two are collinear. And now I have solved FC, so I am left with FB. For that, I cut a section YY like this, and I'm taking the right hand side of the figure. So there is one support reaction here. There are three applied forces here, and from from the section that we have cut, it is intercepting three members, if this C, B, and this member. So I have three unknowns. I have two unknowns basically, because FC we have already solved, and see FC I am drawing into the joint because I have already solved it as compression. And FB and FY I am taking away from the joints. We are assuming it is tension, and this theta is 45 degree from the geometry, you can see, because this is 3 meter, this is also 3 meter. So all the members are inclined at 45 degree from the vertical and horizontal directions. Now I'm considering vertical equilibrium of this portion. So what? Let's see what are the forces I have. This becomes this is in the what horizontal direction, so it doesn't matter. FC is also in the horizontal direction, doesn't matter. So FB has a component cos 45 degree in the along the y direction. Suppose I'm taking downward to be positive. So FB cos 45 is in the downward direction. There is 110 here, another 10 here, another 5 here. So plus 10 plus 10 plus 5, and R2 we solved in the upward direction, so we put it on the other side of the equation. So I'm getting FB by root 2 plus 25 is this, and FB is minus this, so it is a compression. It is a compressive member. So if once I've solved it, if I want to draw this section again, I'm going to put this FB arrow pointing towards the joint B, towards this joint 4. So the three members that I was supposed to solve, A is a zero force member, I have solved B, and I have solved C. So you can see that in each of these portions, what I said initially is, in method of sections, in if I am taking a section, on each half, not half, on each portion we have to solve three equations of equilibrium. But here we only needed to solve one moment equation, right? We had three equations possible, but I could smartly choose such a point that taking moment about that point eliminates all the forces, and I am left with only the force that I am concerned about, FC. So just by writing one equation, solving one equation, I could solve the FC. And similarly in this section, I could take say I could take sigma fxy, so that this force and this force becomes irrelevant, and fb I am solving through just one equation. So that is what is our advantage in method of sections. If you know how to cut, if you are given to solve only certain forces, and if you know how to best cut the section and which equation to choose, you can solve this very fast, much faster than method of joints. So just suppose, just assume that I wanted to solve A, B, and C, and I was solving with the method of joints. Then what would happen? I will solve the support reactions. Then I will first look at this joint, because if you look at any of the joints in the middle, they will have more than two unknowns. So you cannot approach it from the joints in the middle. So I have to choose this joint. Then I have to solve this joint. Then I have to go to this joint. So it will become a much larger process. While I just needed to solve literally two equations to get three. Get these two forces by method of section, so long as I cut the sections properly. Another example, this is a compound truss, as we saw. This is one truss, this is one truss, and they are joined by a hinge. So I'm solving the support reactions first. Ri and Ha, there is a horizontal force. Oh sorry, this is also a hinge. If both of these are hinges, then I have a problem. One second. Let's see. Uh, HA plus HI, I'm taking, assuming both of them pointing towards right. HA plus HI plus 10 is 0. So I know HA plus HI is minus 10. Summation of Fy equal to 0, I get RA plus RI equal to 0. And summation, okay, since this is a compound truss, this is not actually a simple truss. So I can take moment from this side, and I can take moment from the other side to solve the four support reactions. So summation of m I equal to 0. Let's see about this point. I see Ra is applying a moment in the clockwise direction. Ra into 16, 4 plus 4 plus 4 plus 4, and this force 10 is also applying a clockwise moment. So 10 into this distance, so this is 6, 3 plus 3, and this force HA is passing through the line of action of HA is along the I, so it won't give any moment, and RI and HI are about I, so they don't provide any moment either. So I can solve RA and RL here. RA is coming to be minus 3.75, so it means it is in the downward direction, and RI is in the upward direction. And from left, I'm taking MF equal to 0. So at about this point, so this is an internal hinge. We are going to look at that the details later on. This F is an internal hinge. That means that you can take moment, you can conserve moment about any of the two sides. So I'm taking left. This will seem a little confusing right now. We will look at this when we actually go into internal hinges and beams, but for now assume if there is an internal hinge, the way we do the write the equation is, we take moment at that internal hinge from any side, either of the sides, and we will come up with 0. So here I am looking at only the left half. Look, if I am taking looking at only these forces, not the other forces, not RIHI, I am not looking at those. So about F, look at the only, if you look at only left side, RA is providing a clockwise moment. RA into 4 plus 4 8, and HA is providing an anti-clockwise moment with lever arm 6 meter. So minus HA into 6, and 10, this 10 kilonewton is passing through F, so no moment. And these things we are not considering right now. So we get an additional equation here. HA is minus 5 kilonewton. Putting that here, we get HI is also minus 5 kilonewton. So all of both of these are pointing towards left. Now let us consider a section XX here, and I'm looking at the left side, left portion of the truss. So I'm cutting through two members, EF and DF. So I have FEF, FDF pointing away from the joint. So I'm assuming the tension, and I have one force here with two forces here. And now see, when you have solve a force, you can put the sign according to its actual sign. So I know this is downwards. I know this is towards the left. So now I'm writing here. Here when I didn't know the forces, I assumed that HA was towards the right and RA was in the upward direction, but I've got both of those as negative. So now when I'm drawing these, I'm putting it in the opposite directions. HA is towards the left and RA is the downward direction. So sigma Fy equal to 0. What are my y direction forces? I have one 3.75 in the downward direction, and FEF has no component on the y direction, and FDF has a cos component there. So this cos theta, we have to solve, we have to just find out the theta because we know the dimensions. So this is 3, this is 4. You know that the cos theta is 10. The tan theta is basically this. If this is theta, then tan theta is 4 by 3. From that you can get cos as 3 by 5 and sin as 4 by 5. So f df cos theta in the upward, since the component is upward, minus 3.75 is 0. So f df we get as 6.25 kilonewton tension since this is positive. And f sigma fx equal to 0. I have a 10 here, I have a minus 5 here, and then I have FEF and I have the sine component of FDF. So FEF plus 10 minus 5, this will be minus 5, plus FDF sine theta is this. Solving this, we get FEF as minus 10 compression. So and this FDF we have already solved. Okay, so this value we put here. So FDF will be actually be pointing this side. So yes, so that is all. That is how we, here we were, just assume we were asked to solve these two. If I was going by method of joins, I have to start from here, go inside a lot. So method of sections is useful here. If I was just supposed to solve these two, suppose I was asked to solve this, then I might have taken a section like this. You might have to take multiple sections as well. It is not necessary that in any trust, if you're asked to solve any member, it is not necessarily that you just have to cut one section and you can get the solution. You might have to cut multiple sections. You can also use a combination of method of sections and method of joints if needed. But yes, sometimes it really saves time. And that is all for the solving of trusses. I think next class might be beams. So are there any questions? If you don't have any question, you can leave. I'll wait for a few more minutes if anyone has any question.
मैम हेलो।
यस।
वीक 2 का जो असाइनमेंट था
हाँ।
उसका मैम क्वेश्चन नंबर 4 मैम आप प्लीज बता सकती हैं मैम। वो मैम।
अच्छा, मेरे पास नहीं है वो असाइनमेंट, तुम स्क्रीन शेयर कर सकते हो?
ओके।
मैं स्टॉप कर रही
एक मिनट मैम।
हूँ। ठीक है, ठीक है।
मैम स्क्रीन शेयर कर रहा हूँ।
हाँ, करो। अभी तक आया नहीं है। आया था, बीच में फिर से चला गया।
मैम नेटवर्क प्रॉब्लम है।
अच्छा, क्वेश्चन का कोई, अच्छा इधर, इधर तो फोटो नहीं भेजा जा सकता। प्रॉब्लम का टेक्स्ट यहाँ पे लिख सकते हो, या तुम बताओ मुझे कैसा प्रॉब्लम है, मैं फिर कोई हिंट दे सकती हूँ। व्हाट इज द।
मैम मैम क्वेश्चन है चूज द appropriate option of the static inter।
ओके, ओके। हाँ, आई कैन सी इट।
मैम यही क्वेश्चन है।
हाँ, स्टैटिक
क्वेश्चन नंबर 4।
इंडिपेंडेंट। हाँ,
यस।
स्टैटिकली डिटर्मिनेट। हाँ, तो यहाँ पे नंबर ऑफ जॉइंट्स कितने हैं, काउंट करो।
1 2 3।
जॉइंट्स काउंट करना आता है क्या? सी, अगर ऐसे सर्कल सर्कल ना बना हुआ है, देन वी हैव टू एज्यूम दैट एनी any point where two or more members are meeting is a joint. So if अच्छा वो फिर से दिख नहीं रहा. So anyway, that problem had seven joints. Two in the bottom level, two in the top level, and three in the
मैम 7 मैंने काउंट कर लिया
seven,
था
right?
मैम, नेटवर्क की वजह से मैम आवाज नहीं जा
Okay.
रहा था.
Okay, okay, okay. ठीक है, seven. And how many members are there?
मैम 4.
Four members. सबको इंडिविजुअली काउंट करना पड़ेगा. बट एनी नाउ यू हैव आइडेंटिफाइड द जॉइंट्स. तो सारे जॉइंट्स, दो जॉइंट के पेयर ऑफ जॉइंट्स के बीच में जो भी मेंबर है, सबको तुम्हें एक मेंबर काउंट करना पड़ेगा.
ओके मैम, मैं काउंट करता हूँ. 1 2 6. मैम 8.
एट.
यस मैम.
एट मेंबर्स. I think it should be more than 8 because हमारा formula है minimum number of members required for number of joints j is 2j minus 3. वो j यहाँ पे 7 है तो 7 into 2 14 minus 3 11. तो 11 members तो मिनिमम होना ही चाहिए. और एक बार और एक बार शेयर करने का ट्राई करोगे?
मैम मैं काउंट कर रहा हूँ फिर से.
हाँ फिर तो मतलब फिर तो अनस्टेबल आएगा.
मैम 80 तो है.
वेट. 1 2 3 4. देखो ये दो अलग है, ठीक है, यहाँ पे एक जॉइंट है तो दिस इज वन, दिस इज वन, दिस इज वन, दिस इज वन. वैसे काउंट करना पड़ेगा तो 1 2 3 4 5 6 7 8 9 10 11 12. तुम कैसे 8 देख रहे थे? 1 2 3 4 5 6 7 8. 8 मतलब मतलब रीड्रॉ दिस फिगर. वो जॉइंट्स को थोड़ा सा बड़ा बड़ा करके मार्क करके एंड देन every member that is between a joint has to be counted as a separate member. Like this looks like one member but this is actually two members क्योंकि यहाँ पे एक joint है ना. यहाँ पे एक joint है, यहाँ पे एक joint है, यहाँ पे एक joint है. तो ये दो अलग member है. Got it?
यस मैम.
तो 12 टू देर आर 12 मेंबर्स. एंड
ओके.
हमारा वो फॉर्मूला से 2j-3 करके हमें आ रहा कि 2 into 7 - 3 is 11. तो मुझे मिनिमम 11 मेंबर्स चाहिए. इफ़ आई हैव 7 जॉइंट्स मुझे मिनिमम 11 मेंबर्स चाहिए टू मेक इट अ स्टेबल ट्रस. और स्टेबिलिटी से ऊपर, स्टेबिलिटी का मिनिमम रिक्वायरमेंट से ऊपर जितने भी मेंबर्स मेरे एडिशनल है, दैट इज द डिग्री ऑफ इंडिटर्मिनेसी. So I need 11 members. I have 12 members. So this is an indeterminate truss to the order of 1.
ओके
ठीक है, ऑप्शन बी शायद. ओके.
मैम, और 7 नंबर भी, वो भी समझ में नहीं आ रहा है मैम.
ओके.
कि
शुभ.
इसमें मैम इसमें है कि फोर्स ऑफ मेंबर बी ही है, सी 2 मेंबर है. और
हाँ.
इसमें मैम 8 के.
ये असाइनमेंट कहाँ से
मैम
डाउनलोड कर रहे हो तुम?
मैम
वेयर डू यू गाइस डाउनलोड इट फ्रॉम?
मैम वो पीडीएफ, मैम वो असाइनमेंट वीक 2 का असाइनमेंट क्वेश्चन है मैम, जो सबमिट करना था.
अच्छा वो मेरे पास उसका एक्सेस शायद नहीं है. तुम एक बार स्क्रीन शेयर करने का ट्राई करो या शुभजीत हो सकते हो तो करो. प्रॉब्लम 7 आई नीड टू सी द प्रॉब्लम टू सी इट. अदरवाइज अगर तुम्हारा नेट काम कर रहा है तो यू कैन मेल मी द
হ্যাঁ
असाइनमेंट.
ম্যাম, স্ক্রিন তো শেয়ার করা যাচ্ছে।
मैम मैं मेल कर दे रहा हूँ आपको.
हाँ हाँ ठीक है. दिस इज माई मेल आई डी.
ओके.
हाँ. 7.
7 7.
हाँ. ओके. सो Find the force in member BE and member CE of the following truss due to 8 kilonewton load as
न्यूटन.
gravity.
यस मैम.
हाँ, तो बीई और सी, बी एंड सी
सी.
मैंने बोला है। तो अ, हाँ, तो अभी तो मैंने जो मेथड ऑफ जॉइंट्स बोला है, उसमें फर्स्ट तुम्हें पता है क्या मेथड ऑफ जॉइंट्स पहले से पता था? इफ
यस मैम.
तो फिर इसमें प्रॉब्लम क्यों हो रहा है सॉल्व करने? दिस सीम्स अ फेयरली स्ट्रेट फॉरवर्ड प्रॉब्लम। कहाँ पे प्रॉब्लम हुआ था?
मैम वो 8 किलो न्यूटन का मैम जो लोड मैम पड़ा हुआ है,
हाँ,
तो मैम 9.2 किलो न्यूटन कॉम्प्रिहेंसिव कैसे मैम, मतलब वो मैम आइडेंटिफाई उसको मैम कैसे करें? टेंसाइल 9.2 किलोमीटर टेंसाइल का तो मैम वो ठीक है, पर मैम टेंसाइल और कॉम्प्रिहेंसिव 9.2, मैम प्लीज आप थोड़ा बताइए ना.
अच्छा, अच्छा। अब मेरे पास वो लिखने का कुछ नहीं है, लेकिन ठीक है, तुम पेन और पेपर लेके बैठो।
ओके मैम, ठीक है.
आई विल आल्सो टेक। मुझे एक बार असाइनमेंट मेल भी कर देना।
ठीक है मैम.
Shubhajit, if you don't have any doubt, you can leave. I mean, you can stay and listen. You can leave anything.
मैम मैं आपको असाइनमेंट मेल ही कर दे रहा हूँ.
हम्म। थैंक यू।
मैम मैंने मेल कर दिया आपको.
ओके, ओके, तो आई एम शेयरिंग द स्क्रीन देन।
यस मैम.
कैन यू सी दिस?
यस मैम.
ओके, तो फर्स्ट स्टेप है सपोर्ट रिएक्शन सॉल्व करना। सो आर ई एज्यूम कर लेते हैं, आर ए पॉइंटिंग अपवर्ड्स, आर ई पॉइंटिंग अपवर्ड्स, लेट्स एज्यूम। यहाँ पे एक हॉरिजॉन्टल आर एच ए आ सकता है, बट दैट विल बी जीरो बिकॉज देर इज नो हॉरिजॉन्टल फोर्स इन द सिस्टम। ओके,
यस मैम, गॉट इट.
so one equation is RA plus RE is 8 because RA pointing upwards plus RE pointing upwards is 8 pointing downwards.
यस मैम.
And suppose मैं E point के about moment ले रही हूँ, तो
ओके.
RA into 4 is in this sense, clockwise sense में हो रहा है,
यस मैम.
RA into 4 plus 8 into 4 because ये भी इसी clockwise direction में हो रहा है,
ओके.
plus 8 into 4 equal to 0। तो यहाँ से आ रहा है RA is -8
जी.
and RE is 16।
यस मैम.
So okay, I've got this now. So I need BE and CE, right? And तो मैं मेथड ऑफ जॉइंट से जा रही हूँ. आई एम
ठीक
लेट
है.
लेट अस लुक एट दिस जॉइंट फर्स्ट. ए पे आई हैव वन फोर्स एफ ए ई, वन फोर्स एफ ए बी,
जी.
एंड एक ऊपर की तरफ एट, नहीं सॉरी, नीचे नीचे की तरफ एट एट है. तो आई आई नो दैट एफ ए बी साइन 60 डिग्री इज एट. अरे आर यू ऑल्सो सॉल्विंग?
यस मैम.
ओके, सो इधर से एफ ए ई और ए बी क्या आ रहा है?
मैम आपने पॉइंट ए से स्टार्ट किया है ना?
हाँ, पॉइंट ए से स्टार्ट किया है.
मैम. मैम. ओके. मैंने बी से. मैम मैं ई ई को ले सकता हूँ मैम, मतलब फर्स्ट पॉइंट में मैं ई से ले सकता हूँ.
नहीं, तुम ई नहीं ले सकते क्योंकि ई में मेरे चार अननोन है ना. ये
ओके.
मेंबर फोर्स भी अननोन है, ये भी अननोन है, ये भी अननोन है, ये भी अननोन है. और इक्वेशन बस दो है. तो तुम ई को लोगे तो तुम आगे नहीं बढ़ पाओगे उधर उधर से.
ओके.
तुम्हें
ठीक है
ऐसा
मैम.
ही पॉइंट चाहिए जहाँ पे सिर्फ दो अननोन है. इवन बी यू कैन नॉट टेक क्योंकि तीन अननोन है.
ओके.
सो ए लेके सॉल्व करो.
ओके मैम. ट्राई कर रहा हूँ.
हम्म.
मैम आर ई तो 8 into 4/8 करने पे मैम 4 किलो न्यूटन का वो. मैम वर्टिकल लोड जो मैम 8 किलो न्यूटन का है. तो
हाँ.
मैम उसमें वर्टिकल इक्विलिब्रियम यूज करके मैम आर ए प्लस आर ई इक्वल टू 8, आर ए इक्वल टू 4 किलो न्यूटन. तो मैम 4 अपवर्ड की
नहीं
तरफ मैम किलो न्यूटन मैम फोर्स लगेगा और 4 मैम डाउनवर्ड की तरफ.
नहीं नहीं, इधर एक एफ ए ई है, राइट? इधर एक एफ ए बी है.
ओके.
ठीक है. अब इसका मैं वर्टिकल इक्विलिब्रियम ले रही हूँ. तो एफ
जी.
ए ई विल हैव नो कंपोनेंट इन द वर्टिकल डायरेक्शन.
यस मैम.
एंड एफ ए बी का साइन साइन 60 डिग्री ऊपर की तरफ है.
ओके.
सो इट इज एफ ए बी साइन 60 डिग्री इज इक्वल टू 8.
ओके.
डू यू अंडरस्टैंड दैट?
यस मैम.
सो एफ ए बी आई साइन 60 डिग्री इज रूट 3/2. So I get FAB as 16/√3. So it's 9.2 basically. 9.2 tensile. Did you follow it? ठीक है.
मैम मैं सॉल्व कर रहा हूँ.
हाँ हाँ हाँ, करो करो, ठीक है.
मैम मैंने इक्वेशन बनाया है एफ बी इक्वल टू 4/2 2 into sin 60. और मैम
4/2 कहाँ से आ रहा है? नेट.
मैम मैं आपको अपना सोल्यूशन मेल करूँ?
करो करो.
ओके. sin 60 एफ सी sin 60 इक्वल टू 4 since एफ बी इक्वल टू एफ सी ई. तो यहाँ पे हो जाएगा 2f बी ई sin 60 इक्वल टू 4। मैम,
हम्म।
मैम बीई जो है, और मैम ई सी ई आर, वो तो मैम दोनों साइमेट्रिकल है ना मैम?
नहीं, यहाँ पे द स्ट्रक्चर इज सिमेट्रिकल, मतलब द स्ट्रक्चर पार्ट इज सिमेट्रिकल, लेकिन बाउंड्री कंडीशन एंड लोडिंग इज नॉट सिमेट्रिकल। यहाँ पे बाउंड्री
ओके।
कंडीशन अलग है। यहाँ पे लोडिंग इस साइड पे है, इस साइड पे नहीं है, तो वो सिमेट्रिकल नहीं है। A structure symmetry, if there has to be symmetry, there has to be, the members must be symmetrical, the boundary conditions must be symmetrical, and the loading also has to be symmetrical.
गॉट इट मैम। ओके, आई अंडरस्टैंड मैम।
तो हो गया? अच्छा, हो जाएगा। ठीक है।
यस मैम।
एंड इफ देर इज एनी डाउट यू कैन मेल मी एनी टाइम, एनी ऑफ यू।
ओके
ओके।
मैम, एक आउटसाइड का भी प्रॉब्लम है, मतलब मैम वो असाइनमेंट में नहीं मिला है, लेकिन मैम एक क्वेश्चन है मैम, तो उसको वो भी मैम आपको हम भेज सकते हैं क्या?
हाँ हाँ, श्योर श्योर। अभी
थैंक
है?
यू मैम। हाँ मैम, अभी ही मेरे पास है।
ठीक है, मेल करो फिर।
ओके मैं आपको भेज रहा हूँ मैम।
ठीक है।
ये मैम का मेल आईडी
हम्म। हम्म।
शेयर कर रहा हूँ मैम, एक मिनट बस।
मैम असाइनमेंट 2 सॉल्यूशन सेंड करती हो, प्लीज चेक नाउ। कौन सा चेक करना है?
मैम मैंने
क्वेश्चन
शेयर कर
नंबर
दिया
7।
क्वेश्चन।
4। हाँ, শুভজিৎ, বলো কোনটা?
ম্যাম 7-এরটা, যেটা নিয়ে ডিসকাস হচ্ছিল আর কি।
7, okay, okay. So VE is minus 16. If okay, Aman, just wait. I'm looking at question 7. If FTC sin 60 equal to 8. Yes, I think this is fine. The answer has matched. I mean, I'm not checking the calculations, but the approach is fine. Is there any problem with the question? Yes, that I think this is fine. Without checking the calculations, the equations and all are fine. डोंट मतलब ये क्वेश्चन तो बहुत बात का है। इसको अभी मतलब अभी मुझे आई हैव टू ऑल्सो रिवाइज हाउ टू डू दिस द डिस्प्लेसमेंट मैट्रिक्स एंड ऑल दैट, बट वी आर गोइंग टू कवर दिस इन लेटर क्लासेस, ठीक है?
ओके।
अभी मतलब तुम्हारा कोई ये इधर का तो नहीं है ना, एनपीटीएल का तो नहीं है?
नो
मतलब
मैम, ये
बात।
मेरे कॉलेज का है।
अच्छा अच्छा, तो तुम अगर तुम्हें अभी चाहिए तो मतलब मुझे थोड़ा सा इसको लेके पढ़ाई करना पड़ेगा। आई हैव फॉरगॉटन दिस, आई नो दिस, बट आई हैव टू लुक इनटू दिस। ओके।
ओके मैम, थैंक यू।
हाँ, ओके। एनी मोर क्वेश्चंस फ्रॉम आइदर ऑफ यू?
नो मैम। मैम,
हाँ हाँ, बोलो।
आप कौन से कॉलेज से हैं?
मैं आईआईएससी बैंगलोर।
ओके। और कौन से ब्रांच से?
सिविल इंजीनियरिंग।
मैम ऑल्सो।
व्हाट?
मैम,
हाँ
मैं भी सिविल इंजीनियरिंग से ही।
हाँ, सिविल इंजीनियरिंग का ही कोर्स है ना, स्ट्रक्चर एनालिसिस।
यस मैम।
तुम कौन से कॉलेज के हो?
मैम HIT,
फुल फॉर्म?
हल्दिया इंस्टीट्यूट ऑफ टेक्नोलॉजी।
अच्छा अच्छा, तो यू आर सर्टिफाइंग दिस कोर्स?
यस मैम।
ओके ओके ओके, सो if there are no more doubts, I'll end the class.
यस मैम।
Okay, thank you. See you next Tuesday. The next class is on Tuesday. The regular time is Tuesday. This time I had to reschedule it. Okay, I'm ending it.
थैंक यू मैम।